Hello. Hello. Good morning. Today we are going to be doing chapter 10, gases for general chemistry 102, part 2 of general chemistry. And I'm going to share my screen with you, and then we'll go through the details of what we will be studying in this particular chapter. This particular chapter has been divided into 3 units, covering the entire chapter. Each chapter will have its own PowerPoint presentation. Make sure you read the textbook because only the highlights and most important facts about the information that is required is included under the PowerPoint presentations. You are asked to read the chapter from concentrate tricycle, chemistry and chemical reactivity, 11th edition. Starting with that, I'm going to start the PowerPoint presentation itself as a recording. And this will be available to all students as we go along. So, the gas laws and their properties. The important concepts in this particular chapter are factors that affect gases. There are 4 factors that affect gases in their behavior. And so they are as follows: the quantity of gas, which is basically the number of moles, volume of the gas kept in a container expressed in liters, temperature at which the changes are occurring to be written or converted to Kelvin, absolute scale, and pressure. Now, pressure, we are going to do a subdivision for pressure, which is basically pressure and its units and measurement, conversion from one pressure unit to another, followed by the following 5 gas laws that are there in the first part. They are Boyle's law and problems based on it, Charles' law, problems based on it, Guy-Lussac's first law, Avogadro's law, which is usually considered as a hypothesis, and the combined gas equation. Now, the highlights. Highlights of the chapter are as follows. Most important that you have to know is the ideal gas equation and the meaning and the units for each of the terms in the expression, the STP conditions, and the values to derive the gas constant are, as well as how to derive the density of a gas, expression for the molar mass of a gas, knowing molar mass of a compound to derive the molecular formula of a compound if the empirical formula of a compound is given. These are the applications for the ideal gas equation, followed by the Dalton's law of partial pressures, then the Graham's law of diffusion, kinetic theory assumptions, root mean square velocity, and Van der Waals equation, which attempts to model the behavior of real gases by including the correction terms involving the constants A and B to the basic gas equation for an ideal gas, giving rise to the expression P plus A n squared over V squared times V minus NB is equal to nRT. And with that, I'm going to introduce the gases. Why study gases? This is the most important thing. Why not start with, because we know that there are 3 states of matter, why do we still start with the gases? The reason for that we're going to explain. And here, before we go there, the objectives for the chapter 10, unit 1. Describe how pressure measurements are made and the units of pressure, especially atmosphere and millimeters of mercury, are used. The second section deals with the basics of gas laws, Boyle's law, Charles' law, Avogadro's hypothesis, and how to use those laws. So the highlights from the first part of the objectives are given. The Gases are the first substance whose physical properties was explained on the basis of simple laws. They are simple, occur naturally, and exist as single molecules. Many elements and compounds can be converted into their gaseous forms, and therefore it helps to explain the behavior and the properties of gases that are there. Gases, for any trapped sample of a gas, it is possible to measure its mass, volume, pressure, which is a force against the force applied against the walls of the container, viscosity, temperature, rate of conducting heat and sound, rate of effusion, passing through an orifice into another chamber, or rate at which a gas diffuses through another gas or out of a container. Now, these are the properties of the gases that we have discussed before. And so now the next question is, we have to define and calculate what is pressure and how do we measure it. Pressure is defined as force per unit area. It is measured by using a barometer or a manometer. The principle of a barometer is that the height of a liquid in an evacuated column inverted over a container containing the same liquid exerts a pressure equal to the force exerted by the atmosphere on the surface of the liquid in the container. Barometer was invented by Torricelli, in whose name the unit of pressure, torr, is named. Then the manometer is another method of measuring the pressure, and the concept is again the use of difference in pressure, a height to measure the difference in height will equal the pressure that is observed. Difference in the height of mercury levels in mm between the arms of a U-tube equals the difference in torr between the gas pressure and the atmospheric pressure. Equal mercury level is equal to pressure inside and outside are equal. Lower level inside are means gas pressure inside greater than the outside pressure. Lower mercury level in the outer arm implies that the pressure is greater than the external pressure. Atmospheric pressure is greater than the internal pressure. So by using that, we can find out the difference. The units of pressure. The SI unit of pressure is newtons per meter squared, also called as a Pascal in honor of Blaise Pascal. 1 Pascal is equal to 1 Newton divided by meter squared. The standard unit of pressure is 1 atmosphere, and this is converted into 760 millimeters of mercury is equal to 760 torr. 1 bar, it's also equal to 1 bar, 10 to the power 5 pascals, and which is equal to 100 kilopascals. The conversions are given for different units below. And usually when we are solving the problem, this chart is hopefully provided to you, and so you can use it to convert. But at least some of the basic units, it is better to remember. Now for the first example, you're given a pressure. During a hurricane, the pressure drops to 71 centimeter. What is the pressure in atmosphere and bars? So this is a problem based on the conversion. The best example of this is solving these kind of problems is first to convert it to atmospheres and then use the relation between the new unit and 1 atmosphere and get the any change, any new unit for expressing the pressure. We know that, say, we are given 71 centimeters as the gas pressure inside the hurricane. So we convert the atmosphere to 760 mm mercury. We also know that 10 millimeters of mercury 10 millimeters is equal to 1 centimeter. So convert the centimeter to millimeter and then to atmosphere. And so we can do that. So 71 centimeters times 10 millimeters divided by 1 centimeter times 1 atmosphere divided by 760 millimeters, and you get a 0.9342 atmosphere. Or you can also use that 76 centimeters is equal to 1 atmosphere, and therefore 71 centimeters divided by 76 centimeters. You get your ratio and then multiply it by 1 atmosphere. And that fraction is your unit in atmosphere. And same thing for bar. Once you know the atmosphere, we know that 1.01325 bar equals 1 atmosphere and convert it. Now, now we are going to start the 5 gas laws that you are expected to know. And we know that each gas's behavior can be explained in terms of the 4 quantities that are there. And what are they? They are the quantity of gas, which is represented or written in moles, temperature in Kelvin, pressure in the units of atmosphere or any other unit, and volume in milliliters or liters, as the case may be. At the beginning stages, you will find that it is not necessary to convert the pressure into atmosphere because of the way the relationship comes out. And the statement says that the Boyle's law states that for a given quantity of gas, if the temperature is kept constant, then the pressure of a gas is inversely proportional to the volume of the gas. That is P. The pressure is inversely, and inverse means 1 over volume, is constant. And when N and T are constant, what are N and T? N and T are the moles and the temperature. So we can convert this to express this as pressure times volume is equal to a constant BL, standing for the Boyle's law, from which we can say that P1 V1 is equal to P2. And when N and T are constant. From this expression, you see that there are 4 terms. If 3 terms are known, the 4th can be calculated. Furthermore, since volume and pressure occur on both sides of the equation, it is not necessary to convert them into any special unit. Just use the unit that is provided. Now, if you plot the graph, different plots for volume, pressure versus volume, you can see, depending upon how it is, you get an idea how the gas law behaves. Generally speaking, pressure, volume, and concentrate pressure. So we can write 1 over P. Volume is 1 over V versus P, 1 over P. Then you have P versus 1 over V. And this graph of pressure versus 1 over V, we see that 3 of the graphs are linear, and depending upon the nature of the graph. But when you draw pressure versus volume directly, you get a curvilinear graph that is there. But these grasses, these plots are important to interpret the graph, interpret the volume or the pressure at any given time if the number of moles of the gas and temperature are kept constant. So here is an example of a problem based on the Boyle's law. A sample of carbon dioxide has a pressure of 56.5 mmHg and is kept in a 125 milliliter flask. The sample is transferred to a new flask where it has a pressure of 62.3 mmHg at the same temperature. What is the volume of the gas? Hint, of which law is to be used in this problem? The hint for this, as we go along, since numerous laws will come up, you should be able to quickly grasp what the statement states very clearly in the problem. And the hint is we are going to be using the Boyle's law. The hint is that at the same temperature, which means that P1 V1 is equal to P2 V2. And therefore, we know that knowing this, we have to calculate what is the volume in the new flask. The new flask, we are assigning it a volume V2, and therefore P1 times V1 divided by P2 will give us the new volume. And so substituting the values for P1, V1, P2, we can calculate the a volume of the gas. And remember to use the significant figures which you studied in General Chemistry 101, and so write it down. Next is Charles' law. Now the Charles' law, in the relation for Charles' law, the number of moles and the pressure of the gas is kept constant. And the statement states that the volume for a given quantity of gas, the volume of a gas is directly proportional to its absolute temperature, but the pressure is kept constant. Now, because it is directly proportional, we can mathematically write it as volume is directly proportional to temperature. N and P are constant. So we can say that V is equal to KCl times the temperature, capital T for absolute temperature, from which we can write it as V1 over V2 is equal to T1 over T2, or V1 over T1 is equal to V2 over T2. And again, you get four terms. If you know any three of those, and remembering that the temperature must be in absolute units, then we can calculate the whatever term you need. From this, in order to convert a temperature to absolute units, you have to remember that you have to add 273.15 or 273 to the temperature in Celsius. Remember, Fahrenheit if you're given a temperature in Fahrenheit, it must be converted to Celsius, and then you add 273.15 to get the absolute scale. One of the important conclusions from the Boyle's law is that you can actually get the value of the absolute temperature from plotting a volume versus temperature graph at different temperatures for different gases. And from once you plot it, we see that somehow for every gas, you see that at a particular point, the linear graph stops. So first of all, volume versus temperature is a linear graph. And if you plotted temperature, volume versus temperature in Celsius, you will see that for every gas that we know, it stops. All the gases at all temperatures are linear, but they get stopped at a particular point. The question was, why does it get stopped? And the answer to that is very simple, because at that point where it stops, when we cannot measure any volume of a gas, that means the gas has turned to liquid, and so the gas laws cannot apply. And therefore, William Thomson, Lord Kelvin, proposed the absolute temperature by placing minus 273.15 degrees Celsius, and this is called as the zero on the Kelvin temperature scale. How do we get it? Just extrapolated all the linear plots for different gases and saw that they met at a point which it was considered as the absolute zero, or negative 273.15 Celsius. Now, again, an example of a problem based on the Charles law. We're given a 5 ml sample of carbon dioxide enclosed in a gas-tight syringe at 22 degrees. If the syringe is immersed in an ice bath at 0 degrees Celsius, what is the new gas volume? Assuming that the pressure is held constant. Hint for the law. Because the pressure is held constant, we can use the Charles law. What is the Charles law? V1 over T1 is equal to V2 over T2. And what are we looking for? The volume V2 when the syringe is immersed in ice water bath. And therefore, we find that the volume of V2 is actually a product of the initial volume times the ratio of the final temperature over the initial temperature expressed in Kelvin. And so you see that it is 295.15 times divided by 273.15 and then multiplied by 5 and you get the answer 5.4 ml. Next is the Guy-Lussac's first law. The Guy-Lussac's first law gives a relationship between temperature and pressure when the number of moles of a gas and volume are kept constant. This particular law is almost identical to Charles' law, except that now we are keeping volume constant, whereas in Charles' law, pressure was kept constant. And so we find that the mathematical expression is similar. P is directly proportional to the absolute temperature. T, when N and V are kept constant. So we have P is equal to KGL, the constant, times temperature, and leading to the expression P1 over T1 is equal to P2 over T2. Now we have studied three laws that we have studied. And what are they? Combination of the Boyle's law, Charles' law, and the Guy-Lussac's law gives us the combined gas equation when the number of moles of a substance of the gas is kept constant. And so if we combine Charles' law and Boyle's law, and also we can say that you can put in the Guy-Lussac's law, we get that relationship that pressure times volume divided by the absolute temperature is a constant for a set of a number of moles of gas. If you have two sets, then we can say that P1 V1 over T1 is equal to a constant, and that is equal to P2 V2 over a constant T2. And from this, we find that there are 6 terms in this particular expression. Knowing any 5, you can solve for the 6th term. The problems based on the combined gas equation. A sample of a gas kept in a container of volume 25 ml at a temperature of 20.5 degrees Celsius and a pressure of 436.5 mmHg is transferred into a new flask when the pressure changes to 94.3 mmHg at a temperature of 24.5 degrees C. Determine the volume of the new flask. First, check what terms are given. We see that the pressure 1 is given, volume 1 is given, and the temperature T1 in Celsius is given. So convert the temperature to in Celsius to Kelvin. And then we are also given P2 and T2. Do the same thing. Convert the temperature to the degrees to Kelvin, and then substitute in the equation as shown, pressure times volume. So the 36.5 times 25 divided by 293.65 must be equal to 94.3 times V2 divided by 297.65. On rearranging this, we get V2 is equal to 36.5 times 25.0 ml times 293 K divided by 290 times 297.65 K divided by 293.65 K times 94.3 mmHg. Now the units for Kelvin and pressure is cancels out, leaving you only milliliters. And on solving that expression, you get 117.3 ml. Next, the Avogadro's hypothesis. The Avogadro's hypothesis is one of the most important equations or derivations that was obtained in the 18th century, and it gives the relation between the volume of a gas and the number of molecules when the temperature and pressure are kept constant. The statement is that for all equal volumes of different gases at the same temperature and pressure contain the same number of molecules. From this, we can write that volume is directly proportional to N when T the temperature and pressure are kept constant. And therefore, to remove the constant of proportionality, we put in a symbol, constant K, AH, and we see that V is directly proportional to N, KAH times N, from which we follow that V1 over V2 is equal to N1 over N2. The importance of Avogadro's hypothesis is the fact that in calculations, gas volumes is proportional to the amount of gas, so that we can substitute volumes for moles in some stoichiometric problems. And here is an example or demonstration of how we show that you have a gas that is initially has a volume V and it has N. Then if the V increases by twice, then the volume also increases. If the number of moles of gas becomes twice, then naturally the volume also becomes twice. Making our understanding Avogadro's law easier. The volume of a gas is maintained at a specific temperature and pressure, and this is directly proportional to the number of moles of the gas that is there. The mathematical relationship is V is equal to constant times N. Problems based on Avogadro's hypothesis, ethane C2H6 burns it according to the reaction. 2C2H6 plus 7O2 gives you 4CO2 plus 6H2O. The question is, what volume of oxygen is required for complete reaction with 5.2 liters of C2H6 gas? What is the volume of water vapor produced, assuming that all gases are measured at the same temperature and pressure? So the solution is convert the given volume of ethane to volume of oxygen using the mole ratio as shown below, as shown. So we see that for 5.2 liters, we require 7 liters of oxygen. So for 5.2 liters, you will require 5.2 liters times 7 moles of oxygen for 2 liters of C2H6, and that gives you 18.2 liters of oxygen. Next, convert the volume of ethane to moles of water, volume of water, again using the same expression. In the conversion factor, we see that from the expression that 6 moles of water in the gaseous form is obtained for 2 moles of ethane that has been burnt off. And so 5.2 liters of ethane, C2H6 times 6 moles of water divided by 2 moles gives you 15.6. So the problems are very simple. It's just the conditions that one must remember how to use it and apply it. If you forget the hint in the problem, which is already given to you, then you would confuse which gas law to use, and that is the only issue. So make sure you remember the conditions for each of the laws so that it is a quick application and solution. Now, we come to almost towards the end of this particular 5 gas laws that we have studied. And in doing so, we can then find out a very, very important relationship. If we combine all the laws and hypotheses, it gives us a new gas equation called as the ideal gas equation. The term ideal implies that the gases behave ideally or perfectly and follow all the rules. The ideal gas equation gives the relation between the pressure, volume, temperature for a given mass of gas. And therefore, if the given mass of gas is explained in terms of moles, then we can say that the pressure of a gas, the product of the pressure of a gas and its volume is directly proportional to the number of moles of that gas at a particular temperature, where P is the pressure in atmosphere, V is the volume in liters, and T is the temperature in Kelvin. Now, the gas constant, in order to remove the proportionality, we have to introduce the gas constant R. And so then the ideal gas equation becomes PV is equal to nRT. Now, in order to find out how to derive the value of the gas constant, we have to include a certain conditions for deriving the gas constant. And these conditions are called as the standard temperature measured at zero Kelvin, measured at 0 degrees Celsius, 273.15 Kelvin, and pressure of 1 atmosphere. Then if you substitute in the equation, PV is equal to nRT, then for 1 mole of a gas, we get that under STP conditions of 273.15 Kelvin and pressure of 1 atmosphere, all gases occupy a volume of 22.414 liter. This particular volume is called as the gram molecular volume or the molar volume. And using these values for temperature, pressure, and volume of 1 mole of a gas, we get the gas constant as 0.082057 liter atmosphere Kelvin. And you can see that this particular value of 22.414 has been derived and verified by using the various gases at the same temperature of 1 atmosphere pressure, 273.15 degree Kelvin, and for 1 mole of a gas. And we find that the molar volumes for chlorine, carbon dioxide, ammonia, nitrogen, helium, and hydrogen are shown in a plot below, a plot, and then we get to see how accurate our results are. Now, combining Avogadro's law with the general gas equation or the combined gas equation, we get the same expression, PV is equal to nRT. And this is the ideal gas equation. And with this, I have included some practice multiple choice questions, and you can solve them. And with that, I'm going to stop the share.